My name is Akash as an intro. I graduated from Berkeley in the class of 2019, and that's last year. So pretty recent grad. I was co-founder of the blockchain at Berkeley group, and I really enjoyed my time there. And I also really enjoyed being a student. So I'm glad to kind of be back talking to fellow Berkeley alum. I currently work as a software engineer at Anchorage, and that's a digital asset custodian. We're basically building the institutional stack for crypto assets. The way to think about it is we're a tech company like Stripe, and it, there's that, and it meets, I guess, a brokerage on Wall Street, meeting then a crypto conviction about how crypto is going to kind of change the way we operate with money. I like to call it Banks 2.0 in short. I'm happy to answer questions about it after the talk. So why am I giving you this talk? Why isn't someone else just giving it to you? So I worked at a company called Chain not too long ago, summer of 2018 to be exact. And while I was there, it was being acquired by a company called Stellar. Technically, it was being acquired for their for-profit arm called Lightyear, which was owned by Stellar, but you get the point. So I was in New York, and I was sitting with my manager, Dan Robinson, who's this really smart guy when it comes to protocol design. And we were tasked with creating a Lightning Network implementation for the Stellar network. And we managed to get the idea of payment channels working, which is sort of 50% of the way of the Lightning Network. We couldn't figure out how to securely do a full-on Lightning Network implementation without changing the Stellar protocol itself. And that would extend the timeline significantly to ship. It kind of sucks because, the Stellar Foundation had everything they kind of needed to make things happen. They run most of the nodes. So there's some politics here and there. But basically, it's unfortunate that this never really reached production or got finalized into some other project, but it served as a lesson for all of us. Right now, this doesn't really mean much to you, but once I go through this presentation, I think you'll maybe relate to this a bit more. I'd say working on this gave me a lot of exposure to build a simpler version of the Lightning Network. This is kind of like a prototype on the screen of like what we ended up building. We built like a whole wallet plus like a payment channels implementation. But if you ever look at the Lightning Network LND implementation, I'll tell you, it's a beast piece of software. Like it's basically a distributed network system that's designed to handle a bunch of failure cases. And I have mad respect for those people. So, the company now, Interstellar, which was the result of Stellar and Chain, basically merging, or Stellar buying Chain, however you look at it. That company basically has shifted into some very different domains. A lot of the original team left. Last I heard, the company's run by like the co-founder of Zelle, which is like a famous payment system. And I think the goal of Stellar now is to try and replace Swift, which is what I think Ripple kind of wanted to do. But I think we'll see how this turns out. I personally think Libra is going to have a better chance. And this is coming from a person who works at Anchorage, which is sort of partnered in Libra. On top of that, I also just want to share some advice. So I love school. I didn't quite put as much effort into it as some other people did. And, I don't think there's any other place you're going to kind of find an environment where people are focused on just one thing, the practice of academics. It's important to note that theory is like this really awesome thing, right? Like it's fun taking classes, it's fun doing problem sets and reading papers if you're doing grad classes. And most of you are probably computer scientists or studying some form of some technical form of a theoretical subject. Theory is truly infinite. Schools scope it off for us. They give us the roots for pursuing more theory, and depending on your major, sometimes practice, right? But, eventually most of you graduate. Many of you will end up going to some big companies, maybe startups. And the next thing you know, a lot of what you learned isn't being applied anymore. And it's no longer relevant, it gets forgotten. And it really comes down to one thing here. The amount of theory out there is infinite. The number of practical things you could do is finite. You're going to probably spend most of your time thinking about how do I ship this thing? How do I ship this thing? and eventually you'll get stuck in practical land. So while you're here, I encourage you to enjoy learning as much as you can. Take some time to kind of think about this, learn the stuff that other people won't, figure out how to make it practical. I still try to learn theory in my free time. I can't say the same for many of my peers who work in industry these days. But I think something to keep in mind when studying theory is, like, if you aggressively aim to turn it into something practical, you can really make something great. And essentially, this is kind of what the Lightning Network, this is how the Lightning Network kind of came to be. It actually started out as papers. Eventually, it turned into this big, massive project that now Square Crypto is even backing. And other blockchain protocols are taking inspiration from, like Libra and a few others. So I want to talk about the notion of ownership in Bitcoin, because I think a lot of people get confused about this, and it's a little weird coming from the mindset of knowing Ethereum. Here's the dialogue between two people. There's a confused Bitcoiner, and there's the god we all know, Andreas Antonopoulos, who's the author of Mastering Bitcoin. And if you guys know Mastering Bitcoin or even Mastering Ethereum, it's basically the flagship book out there for learning one of the specific subjects in the most detail and practical detail as possible. So basically, confused Bitcoiner is like, how do I own coins? It's under, Andreas responds, it's under your address. The confused Bitcoiner then says, isn't that an account system? Andreas then says, the ledger says you have a specific set of UTXOs. And the confused Bitcoiner says, well, where does it say that, right? So Andreas takes the confused Bitcoiner here to the blockchain, and then he says, UTXO is basically this unopened lockbox that your keys can access. And then the confused Bitcoiner says, like, where does this lockbox even sit, right? It's like, where in this diagram does it even sit? And Andreas then goes to this weird looking JSON thing, and it's actually the transaction. And it's kind of a mess here, but and if you're wondering what the confused Bitcoiner looks like right now, this is exactly what it looks like. But how do I even begin to read this, right? So when we think about transactions, we generally think about updating account balances. It makes sense given we use a bank analogy to often describe the ledger. It makes sense given that Ethereum is kind of easier to understand in that regard. In Bitcoin, more specifically, its data model, there's no notion of an account. There's no notion of balances. There's no notion of coins. There's no recipients, no addresses involved. This is all like higher level abstractions that people have written into the wallet software. And inputs and outputs are actually the backbones of all of this. So if we go back to a transaction, we know that there are many of these in a single block. So let's just zoom into a single one, right? This is really ugly. I just pulled a random one from a block explorer. And I encourage you to do this on your own as an exercise. But if we apply some nice formatting to it, we can take if you look at the fields, we can basically take the VIN and VOUT lists and describe them differently. In particular, we can describe them as inputs and outputs. So inputs and outputs have very important relations. Together, they form the backbone for all state in Bitcoin. In this example transaction, we have one input, two outputs, and wallet softwares are often going to construct a transaction like this if you send something. And in this case, I'm sending money to two different addresses in one transaction. The wallet software will handle what UTXOs use as inputs. So if you ever happen to look in the code in a wallet, this process is actually known as coin selection. It's determining what inputs out of the ones I own can I use. So the birth of Bitcoin is actually the result of outputs. In Bitcoin, outputs make up transaction spending, and in turn, they also make up receiving. There's technically an input, is just to use output. And every Bitcoin transaction creates outputs. When they aren't spent, they're called UTXOs, and that stands for an unspent transaction output. Every transaction represents a change in the global UTXO set. And the UTXO set essentially is just the global set of UTXOs, right? The global collection of it. So when a user's wallet receives Bitcoin, the wallet detects a UTXO that can then be spent with the key controlled by the wallet. When you want to spend, you use an output by referencing it in an input. And this is done by using the TX ID and using its index. So here we have two outputs. And by the way, are there any questions so far? Is everything kind of clear about where we're at? Cool. So here we have two outputs, and here we've denominated them in BTC for just ease of understanding. I'd rather not have large decimals for Satoshis, and a lot of transactions are just Satoshis because one Bitcoin's like thousands of dollars. So outputs contain two parts. They contain an amount, and they contain a cryptographic puzzle that determines the conditions required to spend it, which is under script pub key. Script pub key is basically a locking script. It's the lockbox that's assigned to your to a public key by requiring its corresponding private key signature to unlock it. You can also think of this as a contract. It's a contract that requires a signature to unlock the funds so that I can use it as an input to a transaction. So we're still in a transaction. Let's go back here for a second and let's check on the inputs. Here we have one input. A TX ID is essentially a TX hash, so just keep that in mind. This field is basically used to reference where the UTXO we're using is coming from, transaction history-wise. So in this case, if you look at the TX ID, I'm actually referring to some output of a transaction that had previously happened, right? In this case, the V out is the index that for that output within that transaction, and script sig is basically the inputs that are used to unlock the UTXO. So it's usually the signature that the UTXO is locked to, and as you can probably anticipate, you can do more than just signatures to unlock the UTXO, but we'll get to that. So let's look at the TX ID for that input. And it's on some previous on-chain transaction, you can see below. There's a single output that basically fits nicely for the value of 0.1, which is what this transaction was trying to send, right? If we go back to what this transaction was doing, it was just trying to, the end result, the net result is actually just 0.1 Bitcoin, and it's just sending it to two destinations. So just so happens the input we have is also a nice, I guess, single contained input of value 0.1. Notice that the sum of the outputs happen to be equivalent to the sum of the inputs in this case. In the real world, this isn't always the case, and that's because of fee collection. We'll get into that after this example is done, but for now, let's continue with this. So the output from the old transaction has a script pub key, just like every other output does. Recall that this is a cryptographic puzzle that needs to be satisfied to spend the output. That's what script sig is. It's a signature that basically unlocks the funds. So to kind of recap the notion of inputs, they basically spend outputs, right? They spend the UTXOs. TXID and VOUT refer to which UTXO is being consumed. Script sig is this unlocking script, which is usually some kind of signature input that's used in tandem with the locking script from an output. And script pub key is the stack-based code that lets you unlock the output. And we can, this is kind of, you can refer to this as like the contract. So an example to think about here is, a wallet will usually select UTXOs from what it controls, right? And for each UTXO that is to be consumed to make a payment, the wallet creates one input struct that points to the UTXO and then constructs the unlock script by creating a signature to satisfy the conditions of the locking script. And that's basically how you create input. If you provide a signature that satisfies the locking script and then use that as the input, and then reference the old output, then you can basically use that money. Another thing to keep in mind is there was a field on here called the sequence number for the input. If you look here, that field is, so here it says that it's kind of vague. It says it's used to allow updates to the inputs. What that really means is if the transaction is still in the mempool, let's say you wanted to send the transaction with a higher fee, for example, because the transaction had too low of a fee, and you want this transaction to go through faster because maybe you need to make a trade urgently. Basically, you'll increment the sequence number so that the old sequence numbers are invalid when the transaction goes through. This is a blank slide. Oh, sorry, this is a weird transition. Okay, so inputs, in some transactions, we have Bitcoin that is input but not redeemed in the output. And these are fees collected by a miner. Oops. So I want to talk about a few special cases, actually. Firstly, there's a notion of miner fees, right? We don't know, like when you make a transaction and it goes into a block, right? And the miner is sort of a randomly chosen like winner, right? For every block that gets submitted. How do you choose how the miner gets the funds, right? And the answer to that is you don't. The protocol actually has rules in place for it to choose. So in the case of miner fees, right, the consensus rules will say any input that's not redeemed in the output of a transaction, it essentially goes to the miners. So if let's say my inputs say let's say my inputs are like 0.1, and let's say the sum of my outputs is like 0.9. Or sorry, 0.09. That means the miners are going to get 0.01 in fees. So that's basically how fees work. On top of that, for fees, when a miner submits a block, right, when they win the lottery, they'll include a transaction that has an output to themselves, and that's called the Coinbase transaction. I'll show you what this looks like, but essentially, they'll earn 12.5 BTC. And they'll also 12.5 BTC being the like current block reward, and they'll also include any unredeemed inputs as fee reward in that transaction. And I'll show you an example of this to make it more clear. Another thing to note with inputs is you can actually use inputs from as many addresses as you like in a transaction, as long as you provide the signatures for all those UTXOs. And an example we should think about here, I think that's really important, is what happens if I have 1 BTC UTXO and I only want to give 0.5 BTC? Does anybody have an idea of what kind of transaction we might create? What would the inputs and outputs look like? Let's say the input was like 1 BTC, and what would the outputs look like then?
I can guess.
Sure.
So would you just create a transaction to yourself with the remainder?
Exactly. Yeah, and that's exactly it. You basically create an output that you create an output in the transaction that gives you the remainder. And so let's say I want to give someone else 0.5 BTC, and I want to give myself the change. I might give myself like 0.4 BTC and pay the miner like 0.1 BTC. So explicitly, I'll write an output saying, give me 0.4 BTC under my name, under my public key. Does everything make sense so far?
Akash, I have one question about like fees and kind of how they're like determined and stuff. So
yeah,
like so the way you said in just a basic way, like so the way you said it here is like we know that So the way you said it is like you see like the inputs or something, the outputs or something, and if there's any like difference, like a negative difference in between that means that that's the fee taken. So oh, I don't know what that was, but so then at what stage of the process is the fee kind of like selected? Does like, say if you're like transacting through like your own wallet, does the wallet like set like so you know like, okay, I want to pay around this fee, so then the wallet like creates the transact or like sets this transaction almost in a way that like it already like deducts this fee from the output, and then it like sends these as the things. I'm a little confused about like where the where the fee is kind of set, if that makes sense. Does this make sense? Like,
Yeah. Would it help if I took you through an example of a transaction like on a block explorer?
yeah, for sure.
Because that's my next slide. So I could try
sure.
that.
Yeah. Let's do it. Yeah.
Cool. Let's do that. So I'm gonna go into this little block explorer here, and I basically found some random transactions, that, can you see my screen?
Yeah.
Cool. My monitor's kind of like massive, so I'll try my best to like make this work. Okay, so if we look at this, here's an example of a Coinbase transaction, right? And it's included in this block number. So we're in a transaction. And basically it says Coinbase newly generated coins, and it'll say inputs, it'll say outputs. You'll notice there's no inputs to this transaction, right? A Coinbase transaction's sole value is to just create. It basically just lets the miner who like wins create an arbitrary transaction, and it just has to meet the constraints such that it's the block reward plus whatever the fees are, right? So that's embedded into consensus rules. Does that clear up anything for you, Nishan, or what part is confusing?
I think it makes a little bit. I was just a little confused about like it almost. I know this probably isn't how it is, but it almost made it sound like kind of like the fee was. It's kind of hard to explain. Like the fee.
Are you wondering like how the fee is calculated?
Yeah, almost a little bit, or even like on what side who kind of sets the fee to start it, almost like that maybe.
Yeah,
Maybe that
yeah. So there are quite a few components of fees.
Yeah.
So one part of the fee is there's a fee rate, and the fee rate is set by miners. And the way that's kind of determined is miners just set it to, I believe miners just set it to like whatever they want at a certain given time. I think there are algorithms that kind of run in the background for people to kind of adjust their fee rate based on like how the network is doing, how the load things are. I haven't looked into that code as for specifically setting the fee rate. What I do know is once you have a fee rate, what determines the fee for somebody creating a transaction. So that has to do with the size of the transaction. So the more inputs and the more outputs I have, the greater the fee I have to pay, because the size of my transaction increases and it takes up more space in a block.
Yeah.
Does that make sense?
Yeah. Okay. So then say I'm making a transaction, and then so then basically it's like on your side, whoever's creating the transaction, you know that you'll have to pay like X amount in fees. So you automatically take that out of the outputs when you're creating this transaction, and then you manually take it out of the outputs, and you create this transaction where it's like inputs is 1, and if the fee is like 0.1, then you put outputs at 0.9. The person who's creating the transaction, and then then they know that that's okay. Cool. Okay, yeah, I was thinking like the miner.
So it's kind of weird because like a wallet isn't a wallet. I feel like it's bad programming practice essentially. Like a wallet should kind of be explicit. It should be explicit, right? It should say like, miner gets this fee. I'm guessing they had some discussions as to why that didn't happen, like why they just implied that, the difference in inputs, the sum in inputs and sum of outputs should be the fee. Yeah, it's a good question though.
That makes a lot of sense now though. Thanks.
Yeah, cool. Any other questions?
Yeah, I have a question. So the sequence number, is that used to override any previous mempool transactions that use the same UTXO as an input? Or is there some sort of canonical transaction ID when you submit a transaction that the sequence number then overrides? Because the sequence number has to override based off of something else, right?
Right. That's a good point. So with the sequence number, you are overriding the use of that specific input. So so you saw in the previous diagram, I'll go back to it. You saw in the previous, so here, I boxed this out showing that there's a sequence number per input, and in theory you can have multiple inputs per a transaction, right? So the sequence number is essentially used to override the use of, you can single out like a single input. The only issue is when you do that, the rest of your transaction becomes invalid. So yeah, I mean, you use it to override the specific use of an input, but by doing so, you're actually nulling your previous transaction in the mempool, if that makes sense.
I guess that makes sense if you were trying to update it, but what if you just had a different transaction that has different outputs, but has that input, and then you update the sequence? Because, the input is just an input.
Yeah.
It could be.
It would be the same effect. It would be the same effect, right? Because essentially, you do have a different payload, but the effect on the input, the sequence number that's being read, like is the same. So the outcome would be the same. Okay. Does that make sense?
Yeah, that makes sense. Thank you.
Cool. So we were on a Coinbase transaction. I'm going to walk through a multiple inputs transaction here as well. So if you look at this, you'll notice that there are two inputs to this transaction, right? We can see there's a SIG script, here, and essentially those are the signatures used to satisfy that these UTXOs can be spent. Here we have the outputs, and it's going to this address. And if we look at the amounts, you can see here that there's a difference, and that ends up being the fee. So it's this small amount here. And then let's go into the next example, which is, here's a transaction example with change. And you can see here that this guy this is, I guess, a shorthand view of the inputs and outputs. If we scroll down here, so this address is spending is basically providing these signatures. And if you look here, the outputs are some amount of Bitcoin to some address and some amount of Bitcoin, some amount of change to their address, right? So they basically just gave this person a portion of this output, right? This is how they're able to split the UTXOs, basically. The only way to split a UTXO is you have to use change, or you just don't split the UTXO. So I want to talk about scripts, and we've kind of covered a little bit about scripts, talking about the fields script sig, which is usually the signature, and script pub key, which is usually the locking script or contract per se that we use to unlock things. The thing is with this, most transactions are usually a pay to pub key hash script, and if you've taken the fundamentals course, you've probably seen this. And when a TX is validated, the unlocking script in every single input gets executed by the Bitcoin VM, and then it's executed alongside the UTXO's locking script to see if it satisfies locking condition. So again, this is just saying that the script sig is applied to the script pub key in the previously referenced transaction that it's from. Script is basically the stacked-based language that's designed to run on a range of hardware. It's limited in scope. There's no loops. There's no recursion as a security feature. There's the idea of the halting problem where you could, otherwise run infinite loops. You guys probably know this given Ethereum. There's also the notion of stateless execution. Basically, there's no state prior to the execution of a script. It's not like Ethereum where you can store like a constant variable sitting in a script or a contract. One thing I like to keep in mind is that it's a sequence of opcodes and it's executed in order by stack. I guess it's after the clause arguments are placed on stack, and we're going to see what that really means. I know this might sound like a little bit esoteric. One of the constraints of scripts is that you can't inspect other inputs or outputs in the same transaction. So the contract can't control the flow or value or maintain persistent state, right? So direct control value is also not there. Therefore, I can't restrict how the value we transfer is used in the future. There was a paper that came out like a few years ago on this notion of Bitcoin covenants, which was a potential feature to solve this. Never got implemented in the core, but because we don't have we can't restrict how value is transferred in the future. You can't create stuff like non-fungible tokens. You can't create ERC20s. You can do colored coins, but very constrained in comparison. It's also important to note that Bitcoin script is actually fairly used, right? So in some use cases it's already being used in is multi-signature Bitcoin addresses. There's also time-locked transactions. There's also more complex protocols like payment channels and cross-chain atomic trades, which we'll get into. But reading and writing programs using this is actually pretty difficult. I'll show you why. So here's an easy example of a script, right? This is a good example for mastering Bitcoin. I stole it because I'm kind of lazy to make my own diagrams, but I think it'll set things up for us in a nice way. So this is there's an unlocking script, right? That's the signatures, and there's the locking script, which is in this case it's a pay to pub key hash script. And in order to run through it, right, we're going to start with the unlocking script, which is on the left, right? So the signature is going to be put on top of the stack, and the pub key is going to be put on top of the stack. And the execution pointer just keeps moving to the right. And then after, we have dup being called, which basically duplicates whatever's on top of the stack. So we basically duplicated pub key. And the reason why we did that is so that we take the hash of that, and then we can basically use that to compare with the pub key hash that's included in the script. Oops. And then afterwards, we check if the pub key hashes match. And then the execution pointer moves another step to equal verify. Sorry, equal verify was checking if the pub key hashes match. We move to check sig, which then checks if the signature matches with the pub key that we inputted into the script. And once that happens, we put true on the stack and the script is complete. The Bitcoin VM does not return an error. This is a valid transaction. So this happens for every transaction that gets validated. I want to introduce something that's really neat. It's kind of a dead project, but I think it's something worth knowing for sake of understanding how all this works. Ivy is this smart contract language that was developed at Chain. and it basically lets you compile code from, it basically lets you compile code to Bitcoin script using this high level language. So you can also use, you have this much more expressive language. It lets you use this arbitrary number of like conditions called clauses. And basically what else it does is it makes the script pub key / UTXOs, I'm going to use these interchangeably, it turns them into contracts, right? The way to think of them is actually they're all just contracts. And in order to execute the contract, you just provide inputs, right, to satisfy those contracts. So in order to execute a contract, in this case, for example, right, you'll see there's a clause, and there's like two inputs kind of to instantiate it. So if we look at the two inputs to instantiate it, there's a pub key and a value that basically says, put this much money under this public key, and the only way to unlock it is to follow the clauses below. That's what a contract is saying, right? And there's one clause that we have to satisfy in order to unlock the funds, right, for use in a transaction. So in order to satisfy this clause, if we provide the signature for this public key that is assigned to this contract, then we can basically use the funds in a transaction as an input, right? Does everything make sense so far? I only want to move forward if everything's clear, because it starts to get pretty dense after this. Cool. Also, yeah, I just wanted to say thanks to Dan Robinson, who taught me this stuff and also created much of this related content to the slide, but also created Ivy. It's something that's made Bitcoin very understandable to the point, I think, where an accountant could even understand it. So here's the lock with public key hash example. This was the same example we did for that we stole from Mastering Bitcoin, right? The same exact script, right? Just look at how much easier it is. This code has been expressed in a human readable way, and it's also easier to just like look at it and extend, right? Like I could add more clauses to this. I could add more parties to be involved in this. Here's an example where we might add more parties, right? So here's a contract, and basically there's a sender, there's a recipient, there's an escrow, and there's a delay in a value. So let me explain what this contract does. So this is a contract with more than one clause. And to satisfy the contract, you only need to satisfy one of the clauses, right? That's how you get the value. So escrow with delay basically implements this simple escrow contract. When it's instantiated, you have three keys that get specified. One is for the sender, one is for a transfer. One is for sender, one is for recipient, and one is for the escrow agent, right? The escrow agent basically is this guy who can approve or cancel the transfer with the cooperation of one of the other parties, but he can't steal the money himself. So if the escrow agent and the recipient both failed to cooperate, then after the expiration time, the sender is able to cancel the transfer and recover the money with a timeout clause, right? You can see the timeout clause. There's a duration that has to be met. If you look at the verify older delay line, that has to be met. On top of that, there has to be signatures, right? The signature has to match. You have to have the sender signature match with this. So you can basically imagine variants of this contract, for example, that give the recipient the funds also in the event of a timeout instead of the sender, right, as punishment, because maybe the sender didn't necessarily respond in time. So maybe the recipient should then receive the fund. But you can basically be pretty expressive and modify these contracts to your liking. So I want to take a break. I know this is like pretty dense material. I'll just leave it open for questions, and yeah, feel free to like stretch or whatever.
I have one question. Just it's like a little tangential. So like Ivy Link, it's
Yeah.
basically a language to create like Bitcoin smart contracts.
Yeah, essentially, like it's not really adding anything on top of Bitcoin. You know, the same data
Okay.
gets deployed to the Bitcoin blockchain, right?
Right.
It's just
like
giving
syntactical.
you it's giving you a new way to write Bitcoin script, right? Like this here, like the contract above compiles down into the thing on the bottom.
Yeah, what we were talking about. Cool.
Yeah.
Yeah, so I was just kind of wondering, like, Bitcoin smart contracts, how prevalent are they? Because I mean, I don't hear about them as much or anything, or like right now in like say 2020, are they like a thing
Yeah.
still, or I don't know what the state is. Do you know?
So yeah, in my opinion, the biggest project in Bitcoin is Lightning. And we're going to talk about Lightning
Right.
later in like detail,
Yeah.
but I'd say Lightning is like, you know, the thing that uses Bitcoin scripts in
Okay.
production.
Yeah. I'd gone through
Yeah.
one of those white paper circles on Lightning with Gloria, but so then they use these Bitcoin scripts to like. Okay, that's cool. I didn't make the
Yeah.
connection. That's pretty cool.
Yeah, they use scripts to basically handle everything.
Okay. Oh, so that's how they
Yeah.
handle like the connection with the blockchain. Or like
Kind
how
of, well,
I won't get into it. I think yeah.
So Akash, can you go back to the slide where you stack the unlocking script and the locking script? Oh, I guess it's right here. I've heard that you should not use the same public key to accept multiple transactions because it's not quantum safe. Can you tell us why accepting Bitcoin to the same public key multiple times might not be safe? Or maybe I have that wrong, but can you tell us more about that?
Yeah, I don't know much about the whole quantum safe stuff. I haven't looked into it too much. I have some assumptions as to why, but I guess I'll explain like why it makes sense to sort of shuffle the keys. And a lot of that is just around hiding, essentially. So, you know, if I create a transaction and send money to someone on chain, right? If I reuse the same address, that people will be able to know like how much money I have on chain. And if my address is linkable to like some entity like an exchange, then everyone then more than just the company can know like how much money I have. So like governments can go and like figure out if they get a subpoena, the exchange will know like how much you have, etc. I mean, the exchange by default will probably already know given the KYC AML like stuff, but a lot of the reasons why like wallets will like shift addresses is so that the blockchain transaction history can't be as easily analyzed. So it's sort of like a hiding technique, if that makes sense. It's like a privacy technique. The concern for like quantum computers to like also exchange keys. I don't know. It's been a while since I've like looked at the math for like how long it would take to kind of break a private key. The numbers are basically so large. To sort of guess a private key that like it's more than like the atoms in the universe, right? And maybe a quantum computer can like do maybe quantum computing can do like factoring or potentially like break the discrete log of elliptic curves sooner, right? But I would presume that if you shift keys, you basically keep your Bitcoin on the move. So let's say an attacker like starts hacking let's say an attacker targets a specific like private key and decides I'm going to run like a quantum factoring or I don't know, some quantum algorithm that basically breaks the like discrete log for your public private key pair, right? so that they can discover like what your secret is, like what your private key is. That if I decide to move my funds to a different address at a different at like a given time, whoever's doing that like quantum computing job basically has to start over again, right? They have to basically change their target, right?
It's just like an arms race thing. Like you just have to make them spend enough money that they don't care.
Exactly. Yeah. So it's sort of a, yeah, I don't know how much of the benefit is really there. In practice, I'm not too sure about like the benefits, but in theory, this goes back to like theory and practice. In theory, like, yeah, you could probably like, gain some privacy and security guarantees back. Is how I see it.
Okay, that makes sense.
Yeah.
And for proof of, do you have any thoughts on like proof of burn and the Blockstacks paper? Is that something that has traction or legs? Like, is that something we're looking into for DeFi that's built off of Bitcoin? Because my kind of working assumption is just from an accrued value standpoint, Bitcoin is a little bit more interesting than anything else. And so building decentralized finance off of that, building DeFi is anchored in having some accrued value underneath. So do you have thoughts on that?
Yeah, I have some thoughts on that. Well, first, I think Blockstack has been around for a while, and honestly, I haven't seen much interesting stuff come out of there. It's been like the same problem statement. Seen a lot of people like leave and just move on to new projects.
A lot of churn.
So I would say that if you were looking to work on something Bitcoin related and you want to build like a DeFi like app, a lot of the reason like why Lightning is sort of like a thing is so that people could build apps on top of like the moneyness of like Bitcoin, right? Like that was sort of the intention was like, okay, if you have like some kind of layer 2 global network that lets you do fast transactions and you have like all these interfaces that sort of abstracted away from Bitcoin, maybe in a potentially better way than Bitcoin does, then people can use that to go build their applications, right? I don't know if you've read the paper, like the end-to-end arguments in like network or systems design.
What is that one? End-to-end what?
End-to-end argument. Basically it says like, I mean, you can kind of bend the argument to your will, but basically it's saying that it's best to implement your complex logic at the endpoints and leave like the base layers, like in the case of networking, leave the routers to be like kind of dumb like things without the logic embedded in them. So alternatively, if you don't follow the end-to-end argument on the internet, like every router, like every Cisco, Linksys, Juniper Networks router is like running like applications like Netflix and shit. I won't go into that rabbit hole. But yeah.
Okay, that makes a lot of sense. I'll look into Lightning and what people are doing on top of that. Thank you.
Yeah, I'm happy to talk more about it offline. As it's kind of a detailed topic, like what to work on these days. So yeah, I'm happy to talk to anyone about that. Cool. So I think we can get started again. Are we all good, Minxing?
Yep.
Cool.
Yeah.
Okay. So I want to talk about payment channels. And essentially, payment channels, I've been saying it a lot in this presentation. I'm finally going to describe to you what it is. Basically, it's this off-chain ledger that's kept between two parties. The use case is to do scalable recurring payments. And I think it's something that should be used more by like apps and exchanges, for example. And I've seen and I've talked to people that were kind of like Bitcoin focused companies, like maybe like years ago, But they didn't end up really using payment channels because they've always kind of been a pain in the ass to like implement in production. So it hasn't really been widely deployed, unfortunately. You can think of it as like a two-party consensus when making progress, as opposed to like a standard n-party consensus. And it's usually opened by creating a 2 of 2 multi-sig, and there'll be like a timeout clause similar to like the escrow with timeout, where like if somebody doesn't respond, there's this way of like ensuring that one of the parties can get their fund, the parties can get their funds back. People will describe it in 3 words, right? They'll say it's private. So, what they mean by this is that it shows the net result when you close the payment channel, right? So like the only time people know like the activity of a payment channel is when you open a payment channel, as in you're creating this like 2-party multi-sig contract that you deploy on chain. And when you close the payment channel, when you decide to settle your balances, say, hey, this is how much I have, this is how much you have, right? And then you throw that state on chain, and then your account balances update. It's fast, so all transactions are actually just done through like message passing, and just sharing signatures between those messages, right? And it's cheap. There's no fees except for opening and closing the payment channels. And I know payment channels are still kind of this abstract thing, but we should talk about some of the fundamental things that you should know that allows them to exist, and in turn, this will help. This will help kind of give a framework as to like why they work. So the first thing that allows them to exist is quorums of control. The notion of a multi-sig, right? That you can have M of n. You can kind of have an M of n key setup where like, you just need M parties out of the total n people to just sign off on something for action to happen, right? The other thing is time locks. So in scripts, you have this notion of check lock time verify for actual time, meaning that the script will check will return true if a specific time or block height has been hit, right? That's what it means. And there's check sequence verify, which sets a counter. And essentially you might use this when this will return true based on some counter I could set a counter of like 10 blocks. And then whenever this transaction gets published, that's when the counter starts, right? So it's a relative time lock. So basically a time lock is saying that, it ensures a script can be executed before or after a specific time, right? It'll return true in one of those cases. The fact that we can't double spend allows for payment channels. It's basically the fact that's what allows for blockchain. And non-expiration. So valid transactions don't expire, right? Unless we add things to make them expire, which is a thing. But for this case, I'm just going to say that non-expiration, lets these exist. There's censorship resistance. So private key owner can spend, a private key owner can basically spend a UTXO without being blocked, right? And then there's authentication. So digital signatures are basically, required to have certain addresses manage funds, right? And the fact that we have these, allow for us to sign off on our behalf when it comes to participating in a payment channel. So on the high level, right, a unilateral payment channel, like let's say Alice is paying Bob or someone. The first step is you create a multi-sig between Alice and Bob. It's a 2 of 2 multi-sig, so you require both of their signatures to proceed with any updates. It needs to be timed in the case where somebody potentially goes offline. Step 2, we now need to figure out how to send signable offline transactions. One way to do that is, you set up a direct connection with the person over the internet using the IP protocol. some other ways is like, imagine somebody like Bob, maybe Bob is like a merchant and has like a Square kiosk, right? And with the Square kiosk, you can tap your phones, use NFC. That's how you figure out how to send messages, like offline transaction messages to Bob. And step 3 is that we gotta just hope that script works. So here's a contract. It's called transfer with timeout. And this contract is instantiated with 2 public keys. There's one corresponding to the sender. There's one corresponding to the recipient of some transfer. And this contract can be spent only by the mutual agreement of both parties. So this can be used to create a one-way payment channel. And here's an example. Suppose Alice wants to make some series of payments to Bob, and let's say they're micropayments. Maybe she's browsing like a publication that's owned by Bob, or maybe she's watching a movie that she's paying for by the minute, whatever it is. But she doesn't want to pay a transaction fee for every like one of them, right? For every single one of her micropayments. Alice can basically pre-fund this transfer with timeout with 10 Bitcoin. And she can use her own public key as a sender, and she can use Bob's key as a recipient, right? She could then create a transaction that sends some small portion of the contract, say like some tiny amount of Bitcoin, like I don't know, 10 to the -6 Bitcoin, right, to Bob, and then she sends the rest back to herself, right? Unfortunately, I don't have a diagram for this, but if you imagine what the inputs and outputs look like, right? The input would be 10 Bitcoin, right, from Alice's side. The output would be then 0.001 BTC with this contract, right? And then there'll be change that gets sent back to herself. So she then signs this transaction, right, that we've created with the certain inputs and outputs. But on top of that, she doesn't send it to the blockchain. Bob then only needs to add a signature so that it can claim that tiny amount of Bitcoin that Alice sent, right? But he can also wait for future payments, right? He doesn't have to submit it to the chain. And why is that? It's because that the transaction is still valid because Alice gave a signature. And now given Alice the signature, whenever Bob is ready, Bob can just say, look, I'm going to add my signature, and when I'm ready, I'll just throw it as an input on chain, and then I'll just redeem it, right? I'll just redeem it into like normal BTC. What the actual transaction might look like, and maybe I should use a whiteboard, but if it's unclear, just feel free to ask questions. The transaction would look like something like with a transfer with timeout as the input, right? For redeeming this micropayment on chain, along with a lock with public key hash of that 0.1 BTC that then basically converts the transfer with timeout funds to a lock with public key hash set of funds, right? We're changing the lockbox that these funds sit under when we settle a payment channel, right? Does that make sense so far? Or am I talking too abstract?
Akash, is a good analogy here, like let's say you and I are transacting, and the kind of cost for let's say depositing a check into the bank is pretty high. So we just open a joint account, and then the check needs both our signatures. And when I want to pay you, I just sign it and give it to you. You just hold on to that check, and you can sign it and deposit it later. But then how do you, when I give you another check, how do you like negate the old check?
Yeah, that's a good question. So essentially what we're doing when we make these transactions is, so this is a unilateral payment channel, right? So if I decide I'm going to use a previous transaction, right, I'm actually going to be losing money, right? If I'm the recipient, and let's say like you are like sending me micropayments. If I send you an older transaction state, I'm actually losing money.
Yeah.
On top of that, we can update the sequence numbers. We can use that to sort of help enforce. We can use that to help enforce like what we're doing. But at the end of the day, like there's nothing to stop me from submitting, like as a recipient, from taking a lower number, right? I could in theory take a lower number if I wanted to. This is for the unilateral payment channel case, of course. The bilateral payment channel case where Alice can send Bob funds and Bob can send Alice funds is a lot more like complicated and involved. And in that case, there is a lot of need to think about where the arbitration kind of lies. Like, what are the possible states where Bob can cheat Alice, Alice can cheat Bob? Because if both people can send payments to each other and update collectively their state, then that means either of the parties can try to submit an older state to make things in their favor, right? Does that make sense?
Right, yeah, because you're storing the same net state in two different places. Yeah, that makes sense.
Right. So what happens if Bob disappears, right? Or refuses to sign any transactions? That's exactly what the timeout clause below is for, right? If you look at it, there's like a verify after timeout, right? It's verified that the time has proceeded. There's a verified check sig, checking the sender's pub key and the signature and checking if they match. And then after that clause is satisfied, it unlocks the funds. So, you know, if Bob disappears, Alice can basically call the timeout clause to reclaim all the Bitcoin she used to pre-fund the channel. And this prevents Alice's money from being locked up forever if Bob refuses to cooperate. So this is why it's important to use timed channels. If I didn't have a timeout in this, you know, so a Bob could just disappear and then my funds are gone forever, right? So I made the slide. I mean, it's kind of a joke. I decided not to go through bilateral payment channels. I think it's best left for the reader. I encourage you to kind of think about it. There's a lot of moving parts. But yeah, I'm also happy to talk about it at any given time, maybe after lecture too. So here I want to talk about the primary use case for Litecoin, and that is cross-chain atomic swaps. And, you know, here's an example of an atomic swap. What is it? It's basically saying that we are trying to do an on-chain exchange. Let's say Alice is trying to do an on-chain exchange of Bitcoin to Litecoin, right? So, you know, if you look here, Alice pays 1 Bitcoin to Bob. Bob pays 100 Litecoin to Alice. So the exchange rate is like 1 Bitcoin is 100 Litecoin. These are both on-chain transactions, but in order to do an atomic swap, right? You know, one of us has to go first, right? Alice could pay 1 Bitcoin to Bob, but then Bob could cheat Alice by not making the payment, right? Bob could go first, but then Alice could cheat Bob by not making the payment. So how do you fix this? We need some kind of protocol in place. What if we tried something like a two-phase commit, right? Are you guys familiar with two-phase commits? Have you seen that in classes before?
Yeah.
A little bit, yeah, but maybe it's worth explaining.
Yeah. Yeah. Essentially, a two-phase commit is saying is a way to achieve atomicity, right? It's a way to basically ensure that like a process collectively like happens, right? And I think you'll see what I mean by this once I explain HTLCs. But an HTLC is this thing called a hash time lock contract. And if you've ever looked at the Lightning Network, you've probably heard about them, and maybe you're not quite sure what the heck they do. but they're this means of providing this cross-ledger atomic transaction that we just showed in this example here, right? They're a way of ensuring that, you know, both of these happen, either both of these happen or neither of these happen, right? Because that's the only way that Alice is safe from Bob and Bob is safe from Alice, right? So the way they work is as follows. So you have multiple components, right? You have something called a hash lock. And if you guys are familiar with a commit reveal scheme, anyone familiar with the commit reveal scheme? It's basically where you like hash a preimage and then eventually you reveal preimage and then it shows like it's basically used to like reveal secret.
Yeah.
Yeah. If not, don't worry. This will all become clear very soon. There's time locks, and those act as a failsafe and essentially ensure, you know, that they're basically the timeout clause, right? In this case, we went over a few timeout clauses. It's sort of, this is also there to ensure that a timeout, you know, if funds are locked up, one of the parties can recover them after a given time. So the protocol goes like this, right? You have two parties, and these parties agree to a hashed preimage. And the preimage is known by either the sender or recipient. It can vary depending on, you know, what implementation of HTLCs you're doing. For our case, we'll be having the sender come up with the secret. Secret/preimage is the same thing, so don't get confused. And then they'll agree to an exchange rate, they'll agree to a time lock period, and we'll then set up HTLCs on both the Bitcoin chain and the Litecoin chain. And then when we're ready to transfer, we're going to reveal the preimage, right? And by revealing the preimage, we can then execute both of these operations, right? We can execute both of these simultaneously and ensure that they're going to go through regardless. So this is what the script looks like. And I'm just going to walk you through the script before I walk you through an example. If the dots aren't connecting, don't worry too much. But before an HTLC, so if we look here, right, there is a sender, there's a recipient. We insert their public keys when we instantiate this. We also set an expiration time for this. Usually you'll set this to like, you usually set this to the time it takes to like check if an on-chain transaction has happened, and you'll see why. There's also a hash, right? The hash is actually the hash of that preimage we just talked about in the last slide. And then there's a value. There's a value associated with this. And the value in, you know, in this case, it might be 100 LTC, it might be 1 BTC. We're going to create 2 HTLCs because a single one is not useful on its own, right? It's just a construction that promises to reward a particular recipient for revealing a preimage before a particular time. And that's really like, this is like an esoteric like challenge. Like what does this even mean? Like, why is this even useful, right? So the power really comes here when you have 2 HTLCs, which is the same preimage, right? Which then have staggered timeouts. So, you know, let's look at this example. So, you know, here is an example where Alice wants to swap 1 Bitcoin for Bob's 100 Litecoin, right? What Alice does is Alice locks 1 BTC into a 48-hour HTLC using the hash of Alice's preimage. And Alice is the only one that knows this preimage, right? It's Alice's secret, okay? Bob then locks 100 LTC into a 24-hour HTLC with the same hash. I should say HTLC, not HTC. So now we have 2 HTLCs. We have one on the Bitcoin chain, right? And then we have another on the Litecoin chain. And to keep in mind that in order to create these HTLCs, right, we basically created a transaction with the output, with an output of HTLC created with like parameters instantiated by the contract on the right. Does this all make sense so far? Cool. So, you know, there's a happy case, and basically what this is, you know, Bob will use the secret to complete the Bitcoin HTLC. I don't think I put in here Alice. Alice will also reveal the secret. Okay, so let me clarify a few things, right? So first off, Alice is the one who created the pre-image, right? She knows the secret. Therefore, she has to reveal the secret, right? So the last thing here that we said on the slide is that Alice revealed her pre-image to complete the Litecoin HTLC, meaning that Alice actually is in the state below, right? She's received 100 Litecoin from Bob, right? In the case above, now we have to settle the Bitcoin case in order for this to atomically go through. And, you know, in order to settle the HTLC, the pre-image is now public, right? So Bob can now use the secret to complete the Bitcoin HTLC, right? If we go to this contract here, if you look at what the complete clause has, right? The complete clause contains the pre-image, right? That's Alice's secret that she created. It contains a signature of it contains a signature of the recipient. So in the case of Bitcoin, right, it's Bob. Bob's the recipient. In the case of Litecoin, Alice is the recipient, right? Because we're doing it in exchange. And here, what we did is we basically once Alice decided to reveal the pre-image to complete the Litecoin HTLC, right? She ran through this. She got the value in Litecoin. Bob can then run through the same thing to go and basically activate the HTLC Alice created in order to unlock the value. And then Bob then can receive that value, create a transaction, insert it into a lock with public key hash script or whatever, and it's under his custody now. So this is a good case, right? Bob basically uses a secret to complete the Bitcoin HTLC. Now what happens if Alice doesn't reveal the secret, right? So if Alice doesn't reveal a pre-image, Bob will then just cancel the HTLC after 24 hours, right? We set a timer on the HTLC for 24 hours. And then Alice will also cancel her HTLC after 48 hours, right? Because that's what we set as the timer on the HTLC. If we go back to the script, right, the cancel clause here, if we look at it, all it takes is a signature, right? It just takes a signature from the sender of the HTLC. And in both cases, the sender just didn't respond with the pre-image, right? So because the sender didn't respond with the pre-image, we just resort to cancel so that we can get our funds out. We can cancel what happened in the actual system design. There's a good chance that somebody wasn't trying to be malicious. Maybe just like some software went down and couldn't send a pre-image. So a cancel clause is needed to handle the failure state. So does that make sense about HTLC so far? Are people clear on how an HTLC works?
I'm just wondering if I'm sort of getting it right. So the main security premise, maybe could you go to the previous slide?
Mm-hmm.
So the whole premise is that in order for Alice on the bottom to get that to get 100 Litecoin, then she would have to reveal to Bob something that he can use to get his part of the exchange as well, right?
Yes, that's exactly it, and that's what the pre-image is, right? The pre-image is the shared thing, right? And it's sort of a shared secret that we use for creating both our HTLCs.
Yeah. So this pre-image that Alice is sharing, so so is it the HTLC itself, like it's pre-written into that. It's like guaranteed that if Alice reveals it, Bob will get it. Or are there any, like is it like it's just a security guarantee, or like?
Yeah, that's a really great question.
I'm just wondering, like, are there times like it won't be communicated to Bob or anything like that? Yeah.
Yeah. So let's say, so in the case where like, so it could be a case where, let's say, like Alice decides to reveal the pre-image, right? But she doesn't explicitly send it to Bob. What Bob can then do is, Alice will redeem it on chain through like you remember scriptsig, right? Scriptsig is where we put our inputs. Bob can just go and read what scriptsig is and discover what the pre-image is. So no matter what,
so it's
Bob will have a way. Bob will have a way of getting funds back. Usually it's cooperative, right? So like Alice will send the pre-image to Bob, and then they'll be friendly. But in case they're not, this is designed to like kind of in a trustless way, so that you can go to the chain and just look at it and see, hey, if Alice decided to execute on it, then I get to execute on it too.
Yeah, that makes a lot of sense. So it's like it's right there in the script sig for us.
Yeah.
Cool.
So what else is possible with HTLCs? There's this notion of a cross-chain atomic payment. As you can see, I changed the title. I could create scenarios where I use another currency to pay someone else in their own currency, right? So here's a case where Alice is paying 1 Bitcoin to Bob, but then Bob then decides to pay 100 Litecoin to Charlie. And if the exchange rate is 1 Bitcoin equals 100 Litecoin, I basically have paid 1 Bitcoin's worth in Litecoin to Charlie using this coordination mechanism, right? So this is really cool. Cross payment, and then there's also this notion of cross payment channel atomic payments, right? Like imagine, here we were looking at just like different ledgers. We were looking at Bitcoin and Litecoin. Technically, I don't have to be doing this on chain, right? I could be using the transfer with timeout contract as my accounting mechanism, right? To make these off-chain transfers, keep track of it using offline, like non-broadcasted transactions. And I can make my state updates there, right? I can keep my state updates local. And the cool thing is it translates, right? Because I can then make atomic updates to those local states. And essentially, this is actually what Lightning is doing with Bitcoin, right? Lightning is actually hopping between a bunch of channels with atomic updates, right? It's using trustless updates to hop between a bunch of channels. So none of these payments, go through if one of them fails. So, I've said payment channels here, right? Where Alice is paying 1 Bitcoin to Bob via the payment channel. I'm saying Bob pays 1 Bitcoin to Charlie via the payment channel. I'm saying Charlie pays 1 Bitcoin to Dave via the payment channel. And ultimately, Alice has paid Dave 1 Bitcoin, right, through this whole coordination process. But, I haven't thrown the HTLCs in here that allow you to do the atomic updates between all these. So why don't we try walking through an interesting, potentially real world example as to like how you could do this with like multiple parties, right? So the arrows are kind of, you can imagine the arrows are just like existing payment channels. Like we have been operating on our own ledgers, right? We have this two-party like agreements that are happening for every single transaction that goes through between us. And if you want to think in terms of scripts, it's a transfer with timeout with as a UTXO that's getting updated in the transaction every time you make an update. So let's say we have these parties and they have payment channels. That basically then means the first step will be if Alice wants to send, let's say we want to coordinate a send of 1 Bitcoin from Alice to Visa for this example. The flow of the payment will be Alice is going to lock 1 Bitcoin into an HTLC with Anchorage. And then Anchorage is going to lock 1 Bitcoin into an HTLC with Facebook. And then Facebook's going to lock 1 Bitcoin into an HTLC with Visa. Visa is then going to complete the HTLC, right? And they do that by revealing the pre-image, and they receive the money, right? They receive Facebook's sender, Visa's receiver. Receiver reveals the pre-image and receives money. Facebook's then going to do the same thing. They're going to reveal the pre-image, receive the money. Alice is going to reveal the pre-image, receive the money. And the thing to keep in mind here is once Visa reveals it, it all kind of ripples back, right? You have this kind of ripple like effect that you can see. And if at any point there's kind of a dispute between any of the counterparties, you can go back to the main chain, figure it out. It's a little complex as to how that actually works in a presentation like this, but I've shown you with Bitcoin scripts, you can actually program quite a bit of logic in. And if you read through some of the Lightning docs, and if you look in the repo for like arbitration, like that will lead you to some interesting like leads. But yeah, one way to remember this is like you can think of like the payment completes backward, and the way Lightning kind of strikes is like backward. It starts from the ground and like goes up. So I want to conclude this presentation with one last thing. It's comfortable to be mostly practical or theoretical. If you get really good at connecting the two, you're well on your way to creating like immense wealth. And the reason why I say this, so I think it's pretty sad that people graduate and the pursuit of learning theory kind of like stops, and everything is like kind of known practice, and it doesn't work well for anyone, right? Like it ends up making you more comfortable in like the workforce. Like sure, you can become like a really good engineer, but like if you really want to like stand out and like build something unique, like it's good to like continue to look at theory. We make technological progress when we transition from theory to practice, and we're seeing this with like COVID-19 and everything nowadays, right? This is something that's really difficult to do, and it's why some professors have kind of made millions like doing it, right? Like some professors have started companies and they've actually made it like pretty big. I hope I've striked a balance here in this talk. Though I should definitely try to follow this advice myself. I don't have a coding assignment for you, so I haven't spent much time connecting practical to theoretical as much as I should have. But that said, if you want to pursue this path, I would consider working on open source. I think it's one of the quickest ways to your ideal job if you want to work in this space. So if you look at Square Crypto, for example, like they love Bitcoin, they love Lightning. They've hired some of like the top people in the space to like build out that stuff. Some of the core people who actually originally built out and are core developers in the community. They've hired. Facebook works on Libra. But yeah, there's so many like partner companies that also surround these like two entities as well. So it's like, yeah, if you're looking for stuff to get into, like this is definitely a good jumping off point to consider. Yeah, that's all I had to talk about today. If you have any questions, you feel free to DM on Twitter, send me email. I also do Signal/iMessage. So if you want those details, I'm happy to just email or message you them, whatever works. And I'm happy to chat about jobs in Anchorage, happy to talk about research opportunities in the realm, what open source projects to work on, or just help navigate like the current blockchain market. The amount of theory out there is like, there's so much of it. I think there's only so many things that are practical. So it's like important to keep that in mind when you like pick a project. So where might you go next if you're interested in like learning more stuff? I posted stuff in the resources under the assignment, but if you're curious like more about how to like use Lightning and interact with it and see what the ecosystem is like, you can try out Zap Wallet, which is I think the best wallet out there right now. There's also a mobile version, and it does some fancy stuff with light clients so that you can kind of use it without like attaching your own full node. So that's really cool. Other Bitcoin stuff, there hasn't been that much updates. Like I've seen TBTC, which is like trustless BTC, and there's been some stuff around there integrating, sort of integrating like ETH and like Bitcoin in a unique way. Stands for trustless Bitcoin. They have some kind of like multi-sig setup that involves the ability to generate yields by allowing people to create TBTC. There is also Taproot and Schnorr. These are like nerdy Bitcoin cryptography like enhancements to like the Bitcoin core level system. If you're interested in that, I recommend reading about it. I think it's currently the most, I think it's the most like actively talked about thing in Bitcoin these days for if you're like in the core dev community or if you're like into like what they're working on there. Yeah, otherwise like, you know, check out Lightning, play around with it. I'd say that's kind of where it sort of ends for Bitcoin. Otherwise, like everything else is mostly happening on other networks. And thank you for coming to my talk.
Thank you, Akash.
Thank you.
Cool.
Thank you.